We want to thank everyone for taking the time to join us today. Now, before moving forward with our topic, let me give you a brief introduction about what is Hex-Star Universe. So, Hex-Star Universe is basically a space education and research-based platform which helps students to pursue their careers in the field of space science and technology. We are on the mission of building the biggest community of space science and technology. We give opportunity to the students to work on projects related to space science. Our topic for today is variables. This evening, we have the young talent Teja Begari with us. He is an official ambassador at American Association of Variable Star Observers and an awardee of Global Kids Achievers Award for the category of astronomy. We are really thankful to him for joining us today. So, without any further ado, I would like to request him to proceed with today's topic. Thank you, everyone. This is all from my side.
Uh, all right. Thank you very much. Um, Good evening, everyone. This is Teja Begari. I am currently serving as an ambassador for the American Association of Variable Star Observers and as a research observer. We observe variable stars and we report them to the Aavso. Let's try to understand about what we exactly do. So I've made two PowerPoint presentations today. I would like to share them with you now. Um, 1 minute so I can. Can you see my screen? Can anyone let me know whether they can see my screen or no?
Yes, yes.
All right. Thank you. So I wanted to start up with um, this poster in the first, the variable stars in the AVSO and what you can do. So as mentioned earlier that I'm an ambassador for the AVSO. What exactly is the AVSO and what do we do in the AVSO? So what exactly are these variable stars? I want to answer these three questions today. What are variable stars? And why do we care about variable stars? And how can anyone help and contribute to science by observing variable stars? So a very short introduction to what variable stars are. So the definition of variable stars is quite simple for anyone to understand. Variable stars are those kind of stars whose brightness is not always the same. The stars that vary in their brightness, which means their magnitude as seen from time intervals is not same. Let's say today it's 10.3 magnitude, and tomorrow it might change. It can either become higher or less. So, I mean, brighter or fainter. Some vary just before our eyes, in minutes, hours to days, and some might take even hundreds of days to years. So few variable stars really go in a very smooth cyclic manner, which means there is no variation in their brightness. So a very short overview of variable stars. Maybe you can just make this out, note that variable stars are those kind of stars whose brightness is not always the same and they vary in their brightness as seen from time intervals from the Earth. So I want all of you to just look at this picture carefully. Here, this is a picture from the globular cluster. So you see here a few stars. The brightness is not the same. I mean, let me point to one specific star here. So let's see this. You can see the laser point, and you see this particular star. Its magnitude is not same. It's actually changing its mag. It's not actually blinking. Blinking is a different concept. I mean, twinkling. Twinkling is a different concept. The refraction and all, but this is not actually twinkling. This is something else. Pictures are taken from the VSO. Uh, the there's actually pictures taken every day, and you see that this particular star's um, brightness, the magnitude is not the same. But whereas you see this star, its magnitude is completely same. I mean, there's no change in its magnitude. There are other stars here as well. If we go on counting, it might the session wouldn't be enough. But let's, as keeping myself to time, I'm just showing you this particular star to you. So this is what variable stars are. These are how variable stars are. Their magnitude is not always the same, and they always vary in their brightness. So this is how we actually look at variable stars. We try to understand about them. So this is a Cepheid variable, which is taken from M100. What are Cepheid variables? Let's get to know about them in the coming slides. So this particular picture is taken from April 23rd to May 31st, almost 1 month. So you see here on April 23rd, the star is bright enough. You can see the star. On May 4th, it's a little bit dimmer compared to what it is on May 23rd. On May 9th, it became even more fainter. There's no light at all. I mean, it's completely very fainter. On May 16th, you can hardly see the star. Maybe you cannot see the star at all. You can hardly see that. May 20, you start seeing the star again. It's regaining its brightness, regaining its magnitude. And on May 31st, you see the star at the full magnitude again. So these are the observations made from the AVSO. So these particular observations say that this particular star, a Cepheid variable, is not actually maintaining the same brightness. That is the reason we call them variable stars, because there is a variability in the magnitude. And light curves, these are the graphical representation of the brightness of a star. So you see the vertical axis is the brightness and the horizontal axis is the time. So all the pictures I'm using here are purely from the Aavso database. So, so you see here, magnitude. I mean, you obviously might know that the more the number of the magnitude, the fainter the star. The very less the number of the magnitude. So you see here the magnitude is, let's say, 9, or between 8 and 9. So it's 8.5. So it's very faint, right? And again, for a particular time, it became to 3, which is very bright. So whenever there is a high number in the magnitude, that means the star is very faint. And whenever there is a very low number in the magnitude, that means the star is bright. So you see here, this particular star actually has, so this is for the Cepheid variable from M100. So you see its magnitude is not always the same. It's actually changing its magnitude. And light curves really help us to understand which kind of variable star that is. So talking about the main types of variability, the eclipsing systems, maybe one of my favorite in variable stars. So the eclipsing binaries, or the eclipsing system of variable stars, are two variable stars orbiting each other, which means they revolve around each other. So whenever there are two stars millions of light years away from Earth, we see them to be one single star, right? So if it's too far, we see that to be one. So whenever the let's say we've named here B8 and K2, so it's algal B and algal A. Algal is a binary system of star. So whenever the B8 star comes in front of the K2, which means it blocks its the K2's light. Eclipse in stars is different than what eclipse in planetary system is. So generally, when we talk about planetary systems, what is eclipse? Eclipse is actually something uh, which deals with the shadows. But when it's coming to stars, eclipse is something which deals with the light of the another star. So here you only see the light of the B8 star and not K2 star. So there's a block of magnitude of K2 star, and you see the magnitude of B8 star, which means there is an eclipse which took place, and you see the uh, secondary eclipse. So there's a little change in the magnitude. And whenever there is the K2 star, which is coming in front of the B8 star, so obviously by looking at the picture, you can say that K2 is much more bigger in size than K2. So you do not see the B8 star's magnitude at all, and you see this very huge star's magnitude, and there's a very change in the magnitude, and that is what we call as the primary eclipse. So this is how variable star eclipsing systems are. So what is actually happening here is nothing is happening inside the star. There is no glitch inside the star, but just the light is being blocked by some other star. So nothing actually happens inside the star in eclipsing systems. So these are what eclipsing binaries. Pulsating stars, these are another type of sorry, not binaries, but another type of variable stars. So these are really giant with almost uh, swollen atmospheres that actually pulse in and pulse out. It's actually like breathing, they breathe. So once for a particular time, there's a lot of uh, change in the size, and for another period it completely shrinks. So these are the pulsating systems. So these are the supergiant stars that are incredibly big, which actually weigh as well, and also the the radius is 100 times of the sun. So as you know that solar masses is represented by m dash and o, there's a dot in the middle, so solar masses. So it's actually 100 times of sun radius and also the solar masses. So there's actually a theory, the pulsation theory of variable stars. So it's actually a very big theory. I mean, uh, there are hypotheses, the correction, and all. But Let me just give you a gist of pulsation theory. What exactly the pulsation theory says is the pulsation are due to the instabilities inside the core of the atmosphere of the star. Just because the core is giving out light in a certain amount, the complete star's magnitude is actually being changed. So the core is being pulsed. I mean, it's breathing in and breathing out, and not the complete star. So this is how pulsating stars actually are. Looking at the light curve of pulsating stars, this is a 1200-day light curve of our Leo, and the pulsating red giant varies from 5th magnitude to 11th magnitude, approximately taken in 1 year. So this is how the pulsating variable star exactly are. So you see there's a sudden rise and a sudden um, decrease in the magnitude of the star, and again it it rose again, and there's a decrease. So this is how basically pulsating star variable stars actually are. Cataclysmic variables are another type of variable stars. So these are a kind, I mean, a type of binary stars. But here we have a white dwarf and a red dwarf. So as you already know that white dwarf is much more heavier than that of the red dwarf. So the white dwarf pulls up almost all much material from the red dwarf, which actually forms an accretion disk. So whenever there's this heavy white dwarf takes up a lot of material from the red dwarf, so it forms an accretion disk. And when the hydrogen in the disk suddenly um, crashes, let's say, down onto the white dwarf, there's a lot of energy released in all the wavelengths. So the cataclysmic variables light curve actually explains it really well. So you see, it's completely, there's no actually exact pattern which is being followed. So you see the white dwarf which actually pulls in all the materials from the red dwarf, and you have the light curve like this. So this is 600-day light curve of T-zipper. So very active cataclysmic variables with outbursts every 15 to 19 days. So these are some of the good observations you can actually make, or if you want to. So why are variable stars important? Why do we actually want to understand variable stars? Make us understand the stellar evolution. They help us to understand about the stars, how they are born, how the main sequence life goes on, and how they die. The second thing is that they help us understand about the vast universe, about the cosmic distance ladder, basically. Talking about the first point, the stellar evolution. So they help us to understand the secret lives of stars, how they are born, their life, and the main sequence life, and how they die. Sometimes with a whimper of smoke or a puff, and sometimes violent explosions, which you might know as supernovae, and sometimes might leave behind a black hole or a neutron star. So, talking about black holes and neutron stars, another, of course, interesting topics in astrophysics, Chandrasekhar limit, degeneracy pressure, and all. That's another part of astrophysics, but let's continue with variable stars as of now. So young stellar objects are called as the protostars. So whenever there's a star which is born, I mean a very baby star, let's say, which has just started the nuclear fusion, is called as a protostar. So protostars are often associated with jets. The light curves are not really very in a sequence manner. They're actually very chaotic. So the young stellar objects can also be referred to be variable stars because they evolve. So whenever the stars actually evolve from their births to the main sequence life, there is a change in their magnitude. So we call the young stellar objects as well to be variable stars. Hubble's variable nebula, which is one of the interesting nebula we know, the NGC 2261, also known as the Hubble's variable nebula, is a variable nebula located in the constellation Monoceros. So what's special about this is this complete nebula is consists of variable stars. All right. So we do not see the variable stars themselves. I mean, we do not see the variable stars, but the variable stars actually, as we know, that there's a variability in the variable stars. So due to the increase or decrease of the magnitude, the complete nebula's magnitude as well changes. So that's something very interesting about Hubble's variable nebula. So, which I already said that it's illuminated by the R Armon, which itself we cannot directly see that. So the complete nebula's brightness is changing because of the variable stars inside the nebula. The young supergiant stars, Vivae Canis Majoris, this is one of the largest stars we know. Astronomers estimate its diameter to be 200 times the Sun, and its mass dooms it to a short lifespan. This is basic astrophysics. Whenever there's a star really huge, its lifetime becomes shorter. So if there's a big star, it needs a lot of nuclear fuel. So we know hydrogen is used by stars for nuclear fusion. So if there's a very big star, I mean big by size, um, a lot of nuclear fuel is actually being used by these huge stars, and whenever they end up having complete nuclear fuel, which means that it's very less time for all the fuel to be used. And whenever the star is very, very short, I mean, not exactly short, but small in size, so the lifespan is long. So if the star is big, the lifespan is short. If the star is small, the lifespan is long. Specified variables. One of the interesting variables astronomers, actually observational astronomers at the AVSO, are very fascinated about specified variables. So, which weigh from 3 to 30 solar masses, and which are almost at the end of their phases of their life. So they're about to complete their main sequence life, and depending upon their mass, either might be a white dwarf, a neutron star, or a black hole. So which I earlier said that there's an evolution taking place, and whenever there's an evolution taking place, you see a change in the brightness. So we have specified variables to be variable stars. Binary stars, as I just explained to you, I mean, what exact kind of binary stars are. So stars which are very close and which influence the gravitational and influential development of their partner. So as I earlier said that they are symbiotic variable star and as well as cataclysmic variables. Most of the binary stars end up to be cataclysmic variables because one of the star itself might turn into a white dwarf after its main sequence life is over, and it starts pulling up material from its partner star. And there is a change you notice while you try to collect the light curves. Old age planetary nebulae. So it's actually beautiful. So our planetary nebulae are formed when red giants ejects out layers as clouds of gas, and they leave out only their core and ending up to be a white dwarf. So you see a very great um, ejection and a lot of explosion you see. And 95% of all stars that we see in our galaxy in the Milky Way come from the planetary nebulae. So Sun is also one of them. So something really fascinating thing. Supernovae. So people generally get confused between what are supernovae and what are planetary nebulae. So when you know what supernovae are, you clearly can understand the difference. So supernovae are extremely luminous and cause bursts of radiation that often outshines an entire galaxy. So a typical supernova can radiate as much as energy as the sun is and expected to emit over its entire lifetime. So there are two types of supernovae. So one type 1A and type 1B. So 1A type supernovae are actually those supernovae from the stars which are binaries, and type 2 are individual huge stars. So I have a very great diagram, I mean, a picture of how this actually takes place. So as I said, type 1A and type 1B. So these are the two different types of supernovae. And as you clearly can see, there's a huge rise in the magnitude and just a tremendous fall in the magnitude. And the second thing why we are The cosmic distance ladder. Our knowledge of the universe is very entirely maybe based upon our knowledge of variable stars, from the pulsating Cepheids to the Magellanic Clouds to Type 1a supernovae in the galaxies at the edge of the known universe. So they help us understand the distance to the universe. So yeah, Cepheid variables, the first standard candles in 1908, Mrs. Leavitt discovered the period luminosity relationship in Cepheid variables and the small Magellanic Clouds. So she's one of the well-known, prominent women astrophysicists known. Plunges to the cosmic distance ladder. So this is one of the leading steps to understand about the universe itself. Extragalactic variables. So in 1924, Edwin Hubble used Cepheids to determine the distant galaxy to Andromeda. So uh, he actually saw a Cepheid variable in the Andromeda and trying to calculate how far this variable could be, depending upon the brightness or the variability of the Cepheid variable, and then finally could determine the distance to the Andromeda galaxy. So you see that variable stars are really helping us to understand about the ladder of the universe. So yeah, so it's a beautiful picture. So from Earth to the solar system and nearby stars, Milky Way galaxy and nearby galaxies and distant galaxies. So variable stars really help us to understand about the cosmic distance ladder. All right, how can you help? So there are hundreds and thousands of variable stars. Uh, they're very busy. They do not have a lot of time to observe them or a lot of resources. A new surveys coming online soon will begin to discover hundreds of transit events and new objects per night. Just like 110 years ago, AAVSO observers, um, they have collected a lot of data and that isn't lost. So you can literally help us to in scientific notion and being a scientist by yourself. You don't actually need a BSc level knowledge or even, I mean, you don't even need a very deep knowledge in astronomy to be a part of AAVS. So that is what describes my next PowerPoint presentation about the AAVSO and what you do. So this is one of my, this is basic and important slide of today, the AAVSO and exploring the universe with the AAVSO. So the AAVSO was formed 110 years ago in 1911 out of Harvard College Observatory um, to observe variable stars for the then observatory director, Edward Pickering. So the observers at the AAVSO actually started observing variable stars to understand about the variable stars, and this particular organization was formed exactly to connect professional and non-professional astronomers to collaborate on scientific projects. There are more than 7,000 individuals, both professional and non-professional astronomers at the AAVS roster. So they work upon variable stars who are interested in understanding. So you can actually see that AAVS has become truly international. So we have a lot of people, observers very precisely from different parts of the planet. So there's a mission of the AAVSO. So this is one of my favorite lines of the AAVSO. The mission of the AAVSO is to enable anyone, anywhere, to participate in scientific discovery through variable star astronomy. There are few key points, key words which describe AAVSO. Enable, which means we provide the necessary data, resources, and equal opportunities to everyone despite of their professional interest, whether they are professional or non-professional. We make sure that the resources are used by anyone. That is what is anyone. Equal opportunity will be given to anyone to involve in variable star astronomy and in the AVSO mission, irrespective of their knowledge, socioeconomical background as well. Anywhere, access to the AVSO resources is independent of their geographical location. Doesn't matter from which part of the planet you are. You are very free to and we welcome you to use our resources and be a part of scientific research and participate. This is one of the important uh, words, to participate and to be actively engaged with the AVSO in different ways. There's a lot of things you can actually do at the AVSO. As AVSO is a truly international community, there's a very diverse community. We work with researchers who are very interested to work with the data collected from huge telescopes, learn about them, uh, and help them understand their knowledge in the universe. Also work with observers who are really very dedicated to who observe the variable stars, who collect their magnitude information about variable stars through the telescopes, CCDs, um, DSLR cameras, and even through their binoculars. So you might think, what can an 80-inch or 10-inch telescope on Earth can do to help in the scientific discovery? So professional telescopes, which are really huge, have become really big for professional astronomers to understand about the universe. So observing telescopes of amateur astronomers really help to understand about variable stars, the magnitude, reporting them to the area. So, and we also work with educators who are very interested in educating about variable stars through AVSO to their students, and of course volunteers who make sure that uh, who basically are like educators who um, promote astronomy through AVSO and the variable star astronomy precisely through different webinars, in-person events, online events, or activities. So the AWS international community is really very diverse, and there's a lot of people you can find at the AWS. So as I just showed you, variable stars are everywhere. So the stars whose brightness is changing within time. So you can you this is the picture, the video I've showed you in the previous PowerPoint presentation. Light curves are tools for studying the variable stars. So here you see this particular variable star's magnitude is very constant. It's just 10. There's no change in the magnitude. Whereas you see this variable star whose magnitude actually is changing. So using getting to know about the light curve, we try to understand which kind of variable star that is. Uh, so as I just showed you in the previous PowerPoint presentation about different variability of light curves. So we try to understand which kind of variable star that is. So light curves are the tools for the night sky. Examples of science you can do. So there's a lot you can do at the AVI. So as I just showed you, the eclipsing binaries, you can work upon eclipsing binaries, or you work upon uh, pulsating variables. This is pulsating variables, cataclysmic variables, supernovae, and planetary nebula. An important thing is you can also work on solar database. Of course, with a very safe measure, having a very good qualified solar filter to your telescope and observing the sunspots and reporting them to the area. So that is also available at the area. So because sun is a variable star, so you see a change in the magnitude for about 11 years. Though it's high, you can work upon that. You can be a part of AAVSO and can use the AAVSO resources to understand about the universe. So there's actually alerts given out by AAVSO. There are alerts every time going on. So uh, what exactly are these alerts? So if there's any scientist or any PhD student or any scientist, any professional scientist who is wishing to do their further research, and they do not have a lot of time, they just send a notice to the AVS. So hello AVS, so I need this star's observation. I need the help from the observers at the AVS. So, and the response is really wonderful. So the observers at the AVS. So this is what the alert is given in the website of the target tools. So observers at the AVS will actually learn uh, about that particular alert. Why do the scientists want to learn about it? What are they doing? And every time you make an observation and you send them to the AVS, so weekly you get a mail from the AVS. So, hello, your observations have been really helpful for us. Thank you very much. So and also The more the number of observations you make, you also get your credits to your observations. So the AASO alerts are like campaigns. There are campaigns going every time. So the target tools, stars of interest, you can select your own targets. So this is the AABSO target tool. The link is given here. If you want to get sign into the target tool, please be free to get into the target tool and observe the particular star you would like to. So here in the target tool, let me give you a very brief description about the target tool, how target tool actually works. So the name of the star is actually given, and high priority, which means if there is something like this, a logo like this on the particular star, that means that this star needs to be observed. A high priority needs to be given to this particular star because that is in the campaign. Some scientists want to learn about it. And you have alert notice 454. And once you click on that, you actually get to know about why the scientists want to observe it. What is he or she doing? Or whether they're doing their PhD or they're professionals or they want to observe them for their research. So you can learn about um, the target of the scientist as well. And if there is a blue mark, sorry, a green mark, which means that the star has been observed quite frequently, which means uh, here it said that it was observed 1 day ago, which means it was observed very before. And if that is in red, it means it's not been observed from quite a long time. So you see here it's in 7 months ago. So it's not been observed from quite a long time. And if it is black in color, it says that you cannot observe the star because that's near solar conjunction, which means the other side of the sun. So you obviously cannot observe that particular star. So the target information, which gives you about the constellation, minimum, maximum magnitude. Constellation is really very helpful, important in astronomy precisely. Of course, I'm not talking about the constellations which are used in astrology, but constellations in astronomy are really very helpful to understand about where exactly the star actually is. So the notes and the alerts will be given at the AVSO target tool. So you can just go and sign into the target tool. If you're not yet a member or do not yet have an account at the AVSO, you can go and log in or sign up to your account. Tools for observers, preparation to observe. So all these four tools are very, very important for any observation, any observer of the AVSO. The first tool I'm going to talk about, the variable star plotter, which I feel is the most important tool out of all these four tools, because the variable star plotter gives out information about the magnitude of the comparison star, and there's no magnitude given in the of the variable star because the magnitude changes. Seeing the magnitude of the comparison star, you try to understand what exactly is the magnitude of the variable star. So you compare them. So that is the reason why we call them comparison stars. And once you have just, if there's any particular star you would like to learn about, you can just click on. So let's say Betelgeuse. I'll click on Betelgeuse. So you can just see the magnitude of Betelgeuse. So you can just
Teja, are you saying something? Because if you are, we would like to inform that you are not audible.
Was I not audible from a long time?
For a few minutes, I think.
Okay, I thought I wasn't audible from for a long time, which
Oh, yeah, yeah, it's
scared
fine.
me off. All right, you can still see my screen, right?
Yeah, we can.
All right, thanks. So you can hear me now. Can you hear me
Yeah,
now?
yeah.
All right, thank you. So the JAVSO, maybe this is something you did not hear. So JAVSO is a publication of the Association of Variable Star Observers. So it basically gives out this actually anonymous if they would like to publish their research or new instrumentation, new methods or techniques. They actually have to, maybe it would be really great for them to publish their report at their AVSO. And you have an access to actually learn about them from the JAVSO, the journal, which gives you very recent um, uh, news about what actually is happening in the night sky. So we also have an exoplanet database, which is another complete different part of the AVS. So it's a lot of people at the AVS who are working. So the goal is to observe the long-term light curves of a selective number of exoplanet transits and submitting them to the AVS and learning about them. And another interesting thing is we also have a spectroscopic database, which is one of my favorites. My friend Lauren Hennington, who is my fellow ambassador, actually works a lot on the spectroscopic observation. So if you're someone who is very interested, would like to learn about this particular spectroscopic database, you have a video at the AABS headquarters YouTube channel. So the name of the YouTube channel is AABSO HQ. So where you have a budget spectroscopy and how you can observe and report them. And so recently published publications at the spectroscopic database. So these are ones recently published. So this AV specs, so the AAVSO spectroscopic data. Observing sections, yeah. So this is something everyone, I guess, who are starting their observation should go through. If you are interested in, let's say, I'm interested in ecliptic binaries. They're one of my favorites. I'll have to have complete knowledge on ecliptic binaries to understand how should I observe them and how should I report that to the AVS. So if you would like to learn about, if you are interested in solar observation, you can get to the solar observing section. So there's a lot of observing section, a lot of tools which are interested in observing the variable stars and reporting them to the AAVS. So observing section actually helps a lot of scientists. I mean, observers are obviously a kind of scientists because they do their own research, which means on the complete planet, you're the only one observing that star and helping, being a part of scientific research. So you are a part of scientific research. You can call that to be your own research, and you're giving it to a scientist, which itself has a great honor. The building communities. You can discuss about the softwares, the campaigns, the results at the forums. So these are very helpful. You can with different parts of the planet. So these are actually the forums where most of your doubts gets solved. You can ask any kind of question you have here, and someone or the other will from the headquarters or anyone or any observer will actually give out your answer to your question. And we also have free online events for 2022 or anything uh, related to variable star astronomy. So there's a lot of free online events for you. So you actually can get register for them of the online events from the AAVS web page, www.aavso.org. So if you're not yet a member and would like to be a part of EAVS, so I would somehow convince you to be a member. If you're not even a member, that's totally fine. You can be an observer for free. So the membership is something which helps us to uh, move on for another 110 years. So just so you know, AAVSO is one of the experienced organizations which is 110 years old. Headquarters is in Massachusetts, USA. So Boston, Cambridge, Massachusetts. So, if you're not a member, maybe you can be a member. You can donate to the ABS. So as we continue for another 110 years. If if you somehow want to be a observer, you don't need to be a member precisely. I mean, you can just continue with your observation. And if you have any doubts, please feel free to contact us at aabso@aabso.org. Someone or the other from the headquarters will surely reply to you. And with this, I would really like to end my talk. Join us and let's explore the universe together. Hope you all have clear skies. Thank you.
Thank you, Teja, for your wonderful presentation. Now we would love to move on towards our Q&A session. So if anyone have any problem, please raise your hand and we will allow your mic one at a time and we will call out your name and you can ask Teja your question.
Good evening, sir.
Hmm.
Very good evening. Please continue. You can call me Teja, or every one of you can actually call me Teja. That's fine.
Sir, I am Akriti. I have a question related to stars. Sir, actually, it's about sun. So we know that every in each second, sun burn from hydrogen to helium. Sun converts its energy from hydrogen to helium. So where does sun achieve hydrogen atoms?
Yeah, that's a pretty nice question. So it basically something deals with how stars are formed. So as we know that stars are formed from this huge clouds of gas and dust and interstellar space. Complete hydrogen in the early stages of life, sorry, not the early stages of life, but the early stages of the universe, there was a lot of hydrogen. I mean, how that exactly is hydrogen, that's something which deals with. So a lot of hydrogen atoms ends up to be, under their own gravity. It forms a very nice clump of a protostar, which means a very newborn star. So the amount of hydrogen is actually from the interstellar clouds of dust and gas. So from those you get the hydrogen, and from the nuclear fusion process, the hydrogen gets converted into helium, and not only helium, but once the hydrogen is completely get converted into helium, it gets converted into some other elements as well, which are much more heavier than that of hydrogen and helium. So the core becomes much heavy. So of course, when there is a lot of uh, heaviness, let's talk about a massive star for time being. So if there's a lot of mass in the core, the it contracts. So you see that there is gravitational force from outside, and there is the nuclear fusion from the inside, and that's what keeps the star completely stable. And if there is a lot of mass, the gravity is dominant, and the curvature of space and time. So uh, not really getting into much into general relativity, but the curvature of space and time gives out a black hole. So there's a lot of misconception saying black holes curves space and time, but black holes actually do not curve space and time. But black holes are the ones formed from the result of curvature of space and time, which is done by the core of the star. So I hope I've answered your question. That's how we get the hydrogen from this.
Yes, sir. Thank you, sir.
Sir, I am Kshitij. Are you able to hear me?
Yeah, please continue.
Yes, sir. Then, if the stars means they are very complicated things because the gravity keeps tracking inside and the energy of light keep them means they are crushed outside. So, sir, if means energy or hydrogen of a star or fuel of the star ended up, then what happens, sir?
Okay, let me explain what I got. I mean, I guess your question is what happens if the hydrogen completes, right?
Okay, sir. Yeah.
All right. Yeah. So whenever there's hydrogen completes, I mean, the hydrogen is being converted. There's nothing actually called as completes, but it's being converted to helium. I guess I've just answered the question. If there's a hydrogen is converted into helium, and then the helium is converted into some other elements which are heavier than hydrogen and helium. So it's quite obvious that the mass increases. Gravity is something which is in dominant place right now, and depending upon the mass, whether it could be a white dwarf, a neutron star, or a black hole.
Okay, sir.
Oh,
Thank you.
in a hot sugar than me.
Okay, next, Aradhya Mittal.
Uh, Hi, sir. Sir, I have a question that as a student, how can I become a member of AVSO?
All right. I would. That's a nice question. I mean, you can actually be a member of the AABSO from. You can directly go to the AABSO webpage, which is www.aabso.org, wherein you have a membership form. And I forgot to mention you. There's many things you can actually do having an AABS membership. So what you can actually do is there's a separate series for the members only. It's a complete membership opportunity. If you are a member, you can get very great access to webinars from some of the really well-known scientists. So the last webinar was from Dr. Jill Tarter, which I guess all of you already know her. Dr. Jill Tarter is a wonderfully uh, one of the greatest astrobiologists ever lived. I mean, I guess there's no one much more prominent than her in astrobiology. So last in the last session, she explained about how wonderfully there could be life in the universe, and it was an amazing session actually. So when you are a member at the AVS, so you actually get up a lot of opportunity like that, like the webinars and all. If you would like to be a member, just go to the www.aavso.org. If you want to be an observer, you don't have to be a member. Anyways, if you want to be a member, that's really appreciable. You can go to the www.aavso.org, where you'll be finding complete results.
And sir, how can I become an observer?
Yeah. So if you want to be an observer, you basically need to have an observer code. If you want to do much more, I really appreciate you texting my mail. I'll write the chat. Um, how can I write? How can I text my mail here? The organizer.
In the chat, if you want.
Yeah, yeah, in the chat, yes. That chat and channel meeting is only available to team members. Okay, so maybe you can note down my mail.
Okay, you can send your. We'll write down in the chat. You can. We will write down in the chat.
Okay.
If you want, yeah.
TEJA.
Yeah.
Teja.amb.
AM.
AMB.
B. Yeah.
.aavso
Yeah.
@gmail.com.
All small, right?
Yeah, all small. Teja.amb.avs@gmail.com. So
You can check if it's all right or not.
you have sent to my WhatsApp. Wait a minute.
Yeah, sure.
Um, actually, I'm not getting. It's not in my chat. I mean, okay. I hope everyone here is in the group. The one asked the question, who wants to be an observer. May I please
Yes, sir.
know
Yes,
your
sir.
name?
Yes,
Yeah,
sir.
are
Sir,
you in the group?
yes, sir. I am in the group.
All right. So maybe I can. You can. I'll share my mail ID in the group, anyways, because I'm much more active in the mail. So please feel free to text me on the mail. I'm just sending the mail.
Sure, sir. Thank you, sir.
Yeah, I've just shared the email. You may please check that. Yeah.
Okay, next, Harshvardhan.
Good evening, sir.
Good evening.
Sir, I would like to ask that, as you said that binary systems can also be considered as variable stars. So, uh, would we also consider the cases of blue stragglers and supernova 1A? But in supernova 1A, it is said that the magnitude is always the exact same.
Yeah, I get your question now. So you see, astronomers classify most of the stars known to be variable stars because stars actually go through the process of evolution, which means there is a change in the magnitude. So in a sense, you can say that almost every star is a variable star. But very special thing about the particular variable stars is that, so let's talk about some basic stars. So let's say there's no variability. The main sequence life is being continued without any variability, which means that there is no change in the magnitude. But particularly variable stars, which are asked, binary stars, it's actually nothing is happening inside the star. As I said you earlier, that is an eclipse of the uh, light of some other star coming in front of the another star. So supernovae are actually one of the process and evolution of stars. So once it's about to be supernova, it's going to get brighter, much more brighter, and once it's a supernova, it's completely brighter. So you see, there is a change in the magnitude from one point to another point. There's a change in the magnitude. So we classify that to be a variability in stars. So in a sense, that's a variable star.
Yes,
Supernovae
sir.
are not stars, but the complete, the picture says that there's a variability in the magnitude, right? So that's how we classify them.
Yes, sir. Sir, but in case of special case blue stragglers, sir, there is a very bright star, and in a binary pair with it is a white dwarf. The white dwarf uh, steals material from the more powerful larger star, and then the white dwarf grows more brighter and stronger. So that way, won't it be like a variable star system only?
Yeah, that's
Then
what I
this
showed
would
it in my slides, right? They're called as cataclysmic variables. They're called as cataclysmic variables. Uh, do you want me to get back to the slide again?
no, sir. Thank you, sir.
All right. No problem.
Thank you, sir. That's all.
Yeah, thank you.
Okay, next, Nitesh.
Sir, so my question is that since a star's light takes so long to reach us, how do we know that the star is still there?
Okay, so this is actually it depends upon where the star is. So you see, it takes 8 minutes for light to get from sun. So how long does it take for any star is actually it's you can yourself answer the question, because if the star is quite near, the light takes it takes much less time for the light to come to the observer, and if it is quite far, it takes much long time. So actually observing these stars, we could also find out the age of the universe from the farthest star we knew. We could understand how old the universe actually is. So let's say it took 13.7 billion years for light to come from a star which is around 13 billion light years away. You see, so you see the light has come, it travels so long time. So that's how scientists basically also calculate the age of the universe. So how far a star is, it depends upon how much time the light takes. It's completely depending upon how far the star is.
Okay, I have another doubt. Can I ask?
Yeah, please go ahead.
How long before the expansion of the universe causes our Earth to drift away from the sun?
um so look, this is something very much into the general theory of relativity, I assume, because um the Newtonian mechanics and the Einstein physics are quite different. You see, I could actually give you a very nice example about the, you know, wait a minute. Let me think of a very good example of how different are both of these uh, Newtonian mechanics and general theory of relativity when you calculate the net velocity. So, so let's say you are moving in a particular car and you throw a stone from the car. So what is the net velocity of the stone? Is the speed of the car and as well as the speed of the stone. That is the net velocity. Let's say that to be u and v. The u is the speed of the car and v is the velocity of the stone. Coming to Einsteinian physics, the formula is completely different. So it's u plus v by 1 plus uv by c square. So this is a very huge formula. Um, Here uv by c square. So uv by c square is a really very huge amount that doesn't really count, and 1 plus the really huge amount really doesn't count, and it's going to be 1. So that is the reason why we actually use um, the Newtonian mechanics to understand the textbooks and all. So why actually I said this to you is the time period taken from Earth to actually drift away from Sun is very much into the general theory, the curvature of space and time, I suppose, because the several billion years actually takes. Now you also know that the moon is actually drifting away from Earth. How do we know that? Is It's actually a very nice it's very nicely shown actually, sending a light beam to the moon and the time taken from the light beam to come back. So you have the distance, time and speed formula, and you put up that and you see that the distance is gradually increasing, and therefore you know that it's actually moving away from us. So that's how it is.
Okay, got it. Thanks for answering.
Okay, next, Dakshinamurthy.
Hello, sir. Hello.
Hello, good evening, please go ahead.
Yeah. And sir, may I get the recording of the session if this possible? Is it recorded?
Sure. I guess it's available on YouTube Live. Yeah,
Yeah.
please feel free to share it. You can share it.
Okay.
Yes,
Okay.
Dakshinamurti,
Okay.
it's available on YouTube on the Hex-Star Universe channel. You can go there and watch it.
Okay. Okay. Thank you. Thank you so much.
Okay, next, Thomas Land.
Can you hear me?
Yeah, we can hear you, sir.
Okay. I would, teacher, I would like to clarify an answer to the previous question about expansion of the universe.
Yeah, please go ahead.
Okay. Actually, the expansion's speed, you could say, of the universe depends on distance. And so at the distance to the sun, for example, the expansion speed is very slow. It's actually so slow that you could say that the attracting force of gravity is much stronger, pulls things together much stronger than the expansion of the universe can take things apart. And so actually there is no expansion in the solar system, in the Milky Way, and not even in the local group where the galaxies, the closest galaxies are the Milky Way, Andromeda Galaxy, Triangulum Galaxy. So before, so we know that the expansion of our universe is accelerating. So that means it's expanding ever faster. But before that will be so fast that Earth and the Sun will be separated in some appreciable way. The Sun will not exist anymore, actually. So Sun has just in scare quotes 5.5 billion years left, and then we'll grow to become a red giant, and that will take another maybe 10 million years, 100 million years. But then the sun will dissipate basically, and the question is not a question anymore. So I just wanted to clarify that.
Thank you very much, bro. Just so you know, the participants here, Mr. Lan, Thomas Lan, is an computer scientist and a student of astrophysics at the University of Bern. So thank you very much, bro, for clarifying that particular thing. Thanks a lot.
Yeah, you're welcome.
All right.
Well, next, Dhanashikaran. Okay. Okay, moving on to our next participant, Mayank Kumar Rajbhar.
So, hello everyone. My question is that what's make space so cold? Hello, can you hear me? Hello, hello.
We can hear you.
Okay, so my question is, what what makes space so cold?
Teja, I think your mic is muted. If you are saying something, please check once if.
Oh, I'm sorry.
Yeah.
Sorry. Yeah. So yeah, there's no production of heat nearby. I mean, if there's no production of heat, it's obviously the temperature decreases. So
Oh,
Excuse me, sir. Sir, you told that there is no prediction of heat, but there are many stars which are hot. So why the space is so cold?
yeah, but there's a distance between the stars. So the stars you see in the night sky are not really so close. So they are relative. So the distance is relative. So if you really go near to the star, you do not actually see them to be so close. So if you go away from the sun, you see it is getting much more colder. So the stars you see in the night sky are not really so close as you see. It's, obviously, because distance is relative.
Thank you, sir.
Well, no one else have raised their hand, so I guess they don't have any more questions. So I think we can end our session here. Thank you, Teja, once more for being with us today and spending your precious time with us and helping us all with this wonderful topic. And also thank you everyone, all the participants who have spent their time with us and supported us with this webinar. And also for the more information about the certificate of this webinar, you will get that on the WhatsApp group.
Thank you very much. It's been a really great pleasure for me being here. Thanks again.
Thank you, sir.
Thank you, everyone.
Thank you, sir.
Okay, everyone, you can leave now.